Good morning, everyone, and good morning, Dr. Wenki. My name is Suchana Noidi. I am the master degree student in the program of electrical engineering. So my topic of presentation is Linux-based real-time embedded system. The reason that I choose this final report topic is because I have a side project developing as consumer guitar effects modeling unit, which is used neural amp modeling implement on Linux-based embedded module. In this project, I focused on using the I2S protocol, which is stand for Inter-Integrated Circuit Sound. It's a key technology for transmitting digital audio between integrated circuit compared to alternative like TDM, AC97, the previous sound card before, or USB audio. I2S is simple, has deterministic timing, and support very low latency, which is more important for the real-time audio quality in the digital world. It is typically under 10 milliseconds. That is perfect for application that demand real-time response, such as like a guitar effects or audio interface, like I said. So what is I2S? The I2S was developed by Philips in 1986 and has become an industry standard for nearly 40 years. It's a synchronous serial protocol using just 3 wires: clock, word select, and data to transfer digital audio between chips. IC, because its simplicity and reliability, I2S remain the foundation for most embedded audio systems. So I2S signal structure, there are three main signal in I2S, which is SCK or bit clock for synchronization, WS or word select, left or right channel, and SD, audio data transmission, MSB first. This signal ensure precise timing and channel separation. Let's talk about I2S timing mode. I2S supports several timing modes. Standard mode with one clock delay after WH transition, left justify and right justify mode for different alignment, and PCM DSP mode using single frame synth power. These provide flexibility for various DSP systems. As you can see the timing diagram, the serial clock will become first, and then the serial data will be come after first clock finish, as you can see here. So let's talk about why Linux for real-time audio. Rich ecosystem, ALSA, JACK, major audio framework. It has like so many rich ecosystem. So that's why I use I pick this one. And also it support real-time audio under FreeM, under RT kernel, so to achieve below 10 millisecond latency, and also flexible for developing using Python, C++, and offer built-in I2S driver and DMA support. So let's talk about Linux versus RTOS trade-off. Linux is ideal for complex DSP algorithm, library access, and rapid prototyping. RTOS, however, provide deterministic timing, lower resource use, and simpler debugging, making it suitable for different applications. So the Linux more complex, and so you can put more details and kind of like if you wanna have some more function, so the Linux may be more function, in my opinion. So I choose the NVIDIA Jetson Xavier NX platform. Why? Because I have it developing my project, as I said, with this NVIDIA Jetson, which is so small, and it has a 6-core ARM CPU, 384-core Volta GPU, and 21 TOPS of AI performance. It's run Linux for Traeger, so actually Ubuntu OS, and support ALSA and I2S hardware, which is easy for me to implement, and making it ideal for real-time audio project. So here's some input and output that we can use to communicate with NVIDIA Jetson. So right here you can see. So other than that, without the input interface, we cannot communicate directly to NVIDIA Jetson. We need to use the converter, ADC converter, analog to digital converter. So I decided to use the PCM1808 module, which is easy and so simple. So the PCM1808 ADC provides 24-bit stereo converter or conversion with 99 decibel dynamic range. And also for the DAC, digital to analog converter, which is the output for this project, I use the PCM5102 DAC to convert back digital audio back to analog. So the PCM5102 DAC offers 32-bit output up to 384 kHz with 112 decibel dynamic range. Together, they ensure clean analog to digital and digital to analog conversion for the guitar signal. Okay, let me show you the complete signal chain. So here, as you can see on the left, so it's a guitar input, but actually this one has a buffer to lower the guitar impedance down to the impedance that's suitable to come into the module here. Actually, I use the buffer circuit right here, but I didn't put it on. But actually, I use the in practically I use we call the guitar tuner. So after the guitar, we put the tuner on it. The tuner gonna be the one who can change the guitar impedance, which is very high, into the impedance that's suitable for input for the ADC unit here. So and then right here is the connector at the NVIDIA Jetson, which is I connect them to it. And then the right side is gonna be the DAC unit, digital to analog converter unit. So, and then this output. So the output we can, so as is the PCM 5102 is the module, and it's also built in the earphone amplifier, so you can use the earphone to put your headphone on it, so you don't need to have the external amplifier if you want to use for the in-house, or use for yourself to monitor the sound, or you're playing guitar by yourself without interrupting other people. Then here is a DSP processing chain. So the preamp, overdrive, tone stack, which is adjusting the tone of the like a tone frequency for suitable for the guitar frequency, and speaker in emulation, which is to simulate the guitar speaker sound, and then send to output and send to the earphone. So let's talk about digital signal processing pre-emphasis stage. The first DSP state is the pre-emphasis filter or digital bright switch. If we can say in the guitar world, we can talk about the bright switch. When you connect guitar to the regular amplifier, it's gonna have the bright switch, which is can make the guitar sound brighter. Like they increase the high frequency into the sound of the guitar output. So it attenuated low frequency. So like I said, so it's similar to the real amplifier, which is the bright switch gonna be cut off the low frequency and chip up the high frequency. So by using the the equation y equal to x minus 0.7 x n minus 1. So to tightening the bass and enhancing pick attack clarity. Then we talk about the overdrive section, which is soft clipping overdrive. The soft clipping overdrive use the hyperbolic tangent function y equal to tan h gx to create a smooth tube-like distortion. Tube-like, like a tube sound, like a real amplifier that we use as the tube. If you know the tube amplifier have the real sound, the warm sound, just like that. So to generate the odd harmonic like a real tube amps. So as you can see on the graph of the function of the tan, you can see right here, it's gonna be the soft clipping a little bit. So the sine, which means like an input coming in. So after is part this process of the overdrive by using this formula, equation formula to it, the waveform gonna be have a soft clipping down, gonna have like a little overdrive sound. Next is a tone stack, which is like EQ or like frequency adjust, tone frequency adjust. The tone stack separate bass below 250 Hz, middle 250 to 2000 Hz, and the treble more than 2000 Hz with the independent gain control, similar to analog amp, like EQ section, like I said. So this part is like on the block diagram that you see before. The cabinet simulation, which is like speaker simulation that I told you earlier. The cabinet simulation is gonna be simulate the sound from the speaker as real. We try to simulate the real sound from the guitar speaker. If you can, as you can hear from the real speaker. So we use a first order IIR low pass filter with the 4.5 kilohertz cutoff, simulate natural roll-ups guitar speaker, providing a realistic cabinet response like real speaker. So let's talk about performance metrics. The system run at a 48 kilohertz, 24-bit depth, and 256 sample block to achieve the under 10 millisecond total latency using Python, NumPy, and ALSA frameworks. ARM based, this one is like ARM platform with the I2S support. So for the I2S support, the microcontroller that support I2S is STM32, is a Cortex M4, M7, Nordic, and NXP. The company name NXP, I think. And SBC Linux base is the Jetson Xavier, Raspberry Pi, as you know that, BeagleBone AI. So here's a platform comparison. So the ARM-based SBC like Jetson, Raspberry Pi, BeagleBone support I2S embedded DSP offer low latency. The PC provide flexibility but higher latency. FPGA has an ultra low latency but costly, so much cost. So the cloud thing is massive compute and not a real time. So you have to send up to the cloud and then go back. It's not a real time. So here's a interference and discussion. I2S remains standard due to the simplicity and reliability. ARM-based Linux system can achieve below 10 millisecond latency, suitable for real-time guitar amp simulation. Future work may include AI-enhanced tone, VR, AR audio, and edge computing for smart audio device. So commercial application, as I know in the market right now, that's why I want to build one and launch to the market. This is what in the market right now that using the Linux based Cortex ARM Cortex technology. So the company called Neural DSP, they have the product called Quad Cortex. This is the product that using the combining cloud and neural networking to creating the guitar tone, amplifier tone, and also using the calculation from neural networking, sending to their cloud and come back. They calculate exactly what tone of the guitar amp should be. And then the next one is Kemper amplifier. This one is using similar DSP, but they're using the different technique. They're using the technique called profiler, but it's a real-time system anyway. This one achieve around about 5 to 7 milliseconds, and the Kemper achieve around 8 millisecond latency. So and then for something else, let's say the audio interface. So UA Audio Apollo, this one is you can define as a real-time embedded system too, because it has a DSP inside, and we have to plug it in the guitar right here, and then it's sending out the digital communication to the computer, so to convert the analog to the digital and go to the computer, and you can creating the music using the digital audio workstation software such as like Logic Pro, Pro 2, something like that. So for the reference, I have so many here and also in my report. So this is for the presentation. So I found from the DigiKey for the I2 Embedded Ninja, nvidia.com for finding the Jetson Savier information, including the software and the the software and the development kit, and some idea and so many things in there. And this one is the web page that they have some developer to have like some more idea in there, and edkemper.com, Neural DSP, and uaudio.com for information about the product. So thank you so much for listening to me, and hope you enjoy my presentation. Anything wrong or incorrect information, please let me know, and thank you so much. Have a good day.